Welcome back, ladies and gentlemen. Fourth video in this series, 2D, Newton's third law and eliminating internal forces. So we do have this cool choo-choo train that's pulling along 3 carts, 1, 2, and 3. And each cart has a different mass, 1,000, 2,000, and 3,000. The entire train is accelerating at a mass of 2 meters per second. Assume the craft travel on bearings with negligible friction, so there's no friction involving, so it's just accelerating at a constant 2 meters per second. So as velocity is increasing every second by 2 meters per second, so it starts at 0, then 2 meters per second, then 4 meters per second, then 6, 8 meters per second, then 8 meters per second. It's just at a constant rate of 2 meters per second is the acceleration. I may have stated that incorrect units before I corrected myself there. So the dots below represent the 3 train cars, all free diagrams showing and labeling the forces, not components, exerted on each car. So that means net forces or total resultant forces, not the x and y components. Draw the relative lengths of all vectors to reflect the relative magnitudes of all forces. Each force must be represented by distinct arrows starting and pointing away from the dot. They're very clear on the instructions here. For each diagram, write an equation that relates to horizontal forces in the diagram to acceleration. So acceleration is going to be A. So let's think about this. Forces on the 3,000 kilogram car, 2,000, 1,000, 1, 2, and 3. Well, I'm going to just go ahead and state that since this is the 3,000 kilogram car, it has a normal force still because, you know, the ground is pushing up on the wheels. It's pushing back up, the ground is pushing back up. But also this cart is going to have the equal and opposite force of gravity. And since it starts from the center dot, that represents the 3,000 case. Of course, in the 2,000 case, it's not going to be, the arrow is not going to be that long. It's going to be only 2/3 as long because it goes from 3,000 to 2,000. Normal force of gravity still equal in magnitude, opposite in direction, these two, but comparatively, since this is 3,000, it should be more. This one's the case of only 2,000. Sorry, try and adjust so you can see all 3 together. And then finally, the case of 1,000, 1,000, maybe this will only be 1/3 as long as the original. So normal force, the force of gravity there, just for that 1,000. As you can see, the normal force and force of gravity, it's a good refresher and review from the earlier videos, 2A and 2B, is going to be equal and opposite to the normal force. Except, you know, it's decreasing in this case because the mass of the car is decreasing. Now what about the x components? Now this is where it gets interesting. The third cart, the $3,000 cart, is here on the end and it only feels one force. F3. F3 is literally going to be pulling it. That's going to be that's the force pulling it at the acceleration of 2 meters per second. And so if I have this one, F3 equals the mass of this car, which is 3,000, times my acceleration A. Okay? Now, in this case, what about the second car, car 2? Well, the car 2 feels 2 forces. Force 3 and force 2. So what happens in this case? Well, in this case, force 3 I wrote it here, force 3. These 2 forces should be equal and opposite each other. I mean, they're essentially the same force, but one is pulling this way, one is pulling the other way. It's almost like the whole train is dragging this car at the end, but then it's almost as the rest of the car is being dragged by the mass on the end. And so essentially, we have to understand these 2 forces are going to be the same, except they're in different contexts, as different systems, quote unquote, that we're applying our frame of reference to. But then we still need an acceleration. So that meaning if there's acceleration, there is acceleration. So I want to go over that key in this corner. The acceleration equals 2 meters per second per second. So what does that mean? that the force net does not equal 0. You have an acceleration, so net force can't equal 0. The net force must actually equal something. And so if I'm going to look at this, the sum of my F net is going to be greater than 0. And particularly the sum of my F net in the x. Why in the x? Because it is going to be, it has the acceleration in the x-axis, not in the y. We can see from the y that there is no acceleration in the y. The net force in the y is 0, the acceleration in the y is 0. But if this train is moving along at acceleration of 2 meters per second in the horizontal direction, the positive x, then we do have an acceleration in the x. Our net force is not a 0. Our sum of forces in the x is greater than 0. So if I look at this, I got to remember that, well, because the actual force is coming from the, it's not the caboose, I guess the actual train engine at the front. Then this force F2 on the second cart has to be greater than F3, so that there's still acceleration in the horizontal. There's still a net force positive in the x-axis. And then finally, in that case, from the first train, same thinking. It's not like F2 is going to be different in different locations. No, it's the same. It's just different directions depending on your frame of reference. But now this is F2. My F1, the final force at the end, that is pulling everyone else. Really does need to pull everyone else. F1. So then it cancels out this negative F2 force from this frame of reference, which is really representing dragging the 2,000 kilogram cart, dragging the 3,000 kilogram cart, and then leaving over still some positive force in the x, so it still accelerates. So we can see we need to hold that true across every part of the system. I have a positive net x force. Yes, this negative x cancels some of the positive, but then I still have a net positive overall x force. Yes, this negative x is going to cancel some of the positive x, but then it leaves me over with the exact same. And I was trying to draw this to scale so you can see what cancels out is essentially going to be the same part that this last cart, caboose, feels. If I draw it correctly. Because every part of this system is going to feel that same net acceleration. So I'm literally just showing you the components that are canceling out the overall. And so for each frame of reference, you still are accelerating. You might be feeling different forces because you're at different parts in the system, but you're still going to be accelerating at the same rate because, I mean, at some points you're being pulled by everyone else. At other points you're dragging everyone else. But when you take into account the different forces being applied, we can see that the net force in the x is still the same overall. So then let's look at these equations. This is equations will be, well, F2, which is the positive, minus F3 is going to equal the mass of this cart, 2,000 kilograms, times A. In this case, F1, that's the positive, F1's the positive, minus F2 is going to equal the mass of this car times the stem acceleration, 1,000 kilograms times A. And like we said, this entire train from the beginning was accelerating at a rate of 2 meters per second. So it's not like different carts are going to feel a different A. We're all accelerating at the exact same rate. Now I like this one. This one is interesting because then it says, what are the forces and systems of the 2,000 and 3,000 kilogram cars at the same time? It's almost as if you're taking the 2,000, 3,000 and considering it one whole system together. So that just negates F3. You don't even worry about that. Oh, now you're only worried about F2 because it's like you're dragging the whole thing. So in this case, I mean, since this is a new part B, I'm not going to draw in comparison to other ones because these are different scales. Because individual carts, I'm going to start a new scale and say that if this is my dot here, of course, I'm gonna have a huge vectors here that should be, let me shift things over so you can see. I'll make sure they're equal and opposite in magnitude here. These need to be equal in magnitude but opposite, because then this represents the normal force and the force of gravity mg on an entire system of 5,000. Since it's the 2,000 and the 3,000 at the same time, this is 5,000 people. And since I combined these two cars together, F3 at the end is negated, but is F2 that is still here. I'm running out of disk space on my computer, so I gotta hurry with this video. And so if I consider this is gonna pull forward with an F2 here. F2 is gonna pull that forward. So what this case means when I write the equation, well, F2 is gonna equal my 5,000, because that's the total mass of the system, cars 2,000 kilogram and 3,000 added, times acceleration. Bam. Right? And so if you follow that pattern, and similar to the pattern above here, these ones, hint, 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 I'm checking these on Tuesday, coming up is Monday, these videos will be posted. Please, I'm checking these two. See if you can do that from this video and kind of apply the learning. Now I want to, in this video, I'm going to help solve for F3 and F2, and then in here you're going to be able to solve for F1 if you apply correctly this thinking and the hints from this video. Well, F3 is just this cart times A. F2 is just this cart total mass times A. And so we think about it. Sorry, I gotta show you. My A is 2. So what's my F3? My F3 is gonna be 6,000 newtons. 2 times 3,000 kilograms. What's my F2? My F2 is gonna be 10,000 total. The 5,000 kilograms times the 2 meters per second. So I can go ahead and leave you with that math. If you apply the equation straight up and you apply the acceleration given from the start, F1 question mark, that's on your own. I will be checking that. F2 is going to equal 10,000 newtons. F3 is going to equal this times the 2 meters per second. That's going to equal 6,000 newtons. And so you'll have to do F1 on your own. And in part D, without referencing any math or numbers, explain why F1 is the greatest tension and F3 is the smallest tension, even though F3 is connected to the greatest mass. So, why is F1? Obviously, F1 is going to be greater than these two, and F3 only, the F3 and the force here is only going to feel. How much is it going to feel? It's going to feel the lowest at 6,000. Why is it, even though it's connected to the greatest mass? The mass of the car is 3,000. Why does F1 feel the greatest? Hint, hint, hint. F1 is not just pulling the first car. F1 is pulling how many cars? F3, even though this car is the greatest mass, F3 is only pulling what mass? Think about those words and the forces it is actually dragging in the tension, in that tension, that pulling tension force, to help you answer part D. And that one I leave to you to do on your own. And I'll be checking that from this page. Thank you.